Hello everybody, my name is Prashant Venkatramana and I'm here to talk to you as part of this lecture series on modern construction materials. My topic would be glass. Today we see glass being used extensively in buildings across cities especially. Now glass can be, apart from being fascinating, it can be extremely beneficial if used carefully. Let's see how as we proceed through this lecture. Just to give you a short introduction of myself, I'm a mechanical engineer by profession, and I hold a postgraduate degree in engineering for sustainable development. I worked with the Ministry of New and Renewable Energy with their green rating in integrated habitat assessment and with the Indian Green Building Council as an accredited professional. I work with Saint-Gobain Glass India to provide technical support to architects, consultants and fabricators in the Middle East, Africa and in Sri Lanka. A little bit about Saint-Gobain Glass. The company was founded in 1665. It's part of the 42 billion euro Saint-Gobain group, which is engaged mostly in the construction industry. We do construction materials, glass, packaging, performance materials, plastics, ceramics and abrasives, apart from specialized materials. The group mission is to be a reference for sustainable habitats. Moving on to today's agenda. What I'm going to talk to you is about the history of glass manufacture, about the advantages, how glass can be beneficial in your buildings, a little bit about the role of glass in modern architecture, the role of glass in sustainability and bringing about sustainable design in the built environment, safety, and then we'll summarize. Glass manufacture. Glass was found as early as human civilization in natural occurrences such as meteorite. I'll just start again from the beginning here. It's cut. Yeah. The first known manufacture of glass or glass making evidence was found in Mesopotamia in 3000 BC. Now before this, naturally occurring glass was found in meteorite sites. In our region, that is South Asia, the first known evidence was around 1730 BC. By 1500 BC, in the Middle East and in Egypt, extensive glass production, especially in the use of ornaments, has been noticed. Now, just to give you an example, in Egypt, where mummification was a practice and ornaments and valuables were buried along with mummies, there has been many instances where glass has been found to be one of these valuables. 650 BC was the first glass making manual. By the 14th century, when glass became more and more common and the use of glass in buildings started, Murano in Italy became the center of glass making. 1665 was when Saint-Gobain started the glass manufacture in France. In the 1930s, the sheet and plate process began, and in 1959, the most widespread manufactured process, that is the float glass process, was invented. The float glass process. Most of the glass you see today in your buildings is manufactured by the float glass process. Now, a float line can be 600 meters long and can go up to 1 kilometer long in some instances. This consists of five main areas if you look at the entire line. You start with the batch where the raw materials are processed and created in small piles of known weight and volume, which move on to the furnace. In the furnace is where the melting of glass takes place. This moves on to the special area, the float, which is unique to the float glass process. The glass is floated over molten tin and a ribbon is formed because of the difference in densities. Now this ribbon is moved on to rollers in the annealing layer. The annealing layer is extremely long and can be even as long as 400 meters. This is where the slow controlled cooling of the glass takes place. It begins at 600 degrees at the beginning of the layer and goes up to down to 40 degrees centigrade. This moves on to the cold end, where the glass is cut, optimized, and then stacked. Just about the raw materials that go into the manufacture of glass. Glass is fascinating as it uses more of earth materials, most of which is sand. Sand brings in silica, which is found up to 95 to 99% in normal occurring sand. Its melting temperature is 1750 degrees. The other raw materials are limestone, dolomite, soda ash, sodium sulfate, and coke. Some of these are used as fluxes, and some of these are used as refining agents. These are to bring about calcium, magnesium, sodium, and to carry out the oxy-reduction reaction in the furnace. You can understand this better if you look at the final composition of glass, wherein you have silica, calcium oxide, sodium oxide, alumina, magnesium, and potassium oxide in their respective compositions. A glass is a unique material which has the structure observed in a supercooled liquid, but exhibits the mechanical properties of a solid. More on these mechanical properties would be explained during the design of glass. Why do we use glass in buildings? Why do we see glass everywhere today? Let's have a look at that now. Glass has become indispensable to modern architecture. Why? One, it saves time. Glass is much faster in construction. You can do an area of 150 square meters in a single day. It's a lighter material. It saves resources, a sum of 1,300, which includes, let's say for every 15 floors, about 500 in the brick material and the remaining 800 in the foundation removal and additions. So this saves resources. It's energy efficient. A 9% minimum energy demand reduction is observed in a building between buildings which use glass and do not use glass. Now this can go up to as much as 50% or even higher if you use glass effectively and carefully. We will touch upon this especially in the coming slides in this lecture. Another unique property of glass is that it's transparent. It brings in daylight to the interiors and blends the interiors with the exteriors. This has also been seen to improve productivity as compared to the claustrophobic effect you get without the windows. No other building material can effectively do this when being fully transparent as glass with such a high light transmission. Just to show you some examples of buildings which combine natural and artificial lighting in these slides. And in the next slides, buildings which use only natural daylight through effective daylighting devices, as the picture you see on the right, and completely glazed windows which allow light inside but reject the heat transfer between the window. Apart from that, glass is also recyclable, most of which is used in the manufacture process itself and can be reused in the annealed condition, where it can be cut and reused again, or as full windows. Architecture. Let's see how glass plays a role in today's architecture, how glass has evolved over the days. If we look at modern architecture, you can divide them into generations. In the first generation, windows were smaller, what we call punch windows, and glazing wasn't extensive. You move on to the second generation, the skyscrapers used fully glazed facades, wherein the entire character of the building was known through the glass. In the third generation, transparency became more important, and glass was seen as a material that could give a sense of openness. The fourth generation was more about form, using the form of the building to actually provide function in terms of passive design in architecture. The fifth generation, what we are moving towards, is communicating through the entire facade through glass, wherein you can actually use the glass to provide a function apart from its standard functions of transparency, heat reduction, and structural. Let me show you some examples of the fifth generation, because this can be quite interesting. Example number 1, electrochromic glass. This is an example in Ball State University in the USA. If you look at the present picture, there is 60% light transmission in the glass. So there is a lot of light coming in. When the sun moves exactly over this roof, there would be the issue of glare in the building. Now the glass itself can switch in tint. From the 60%, the glass moves to 2%, optimizing the amount of light coming inside. Now the issue of glare is removed and the light that was available outside becomes usable in the interiors. Another example in Shabbat College in the USA. Another example in Saudi Arabia, where the glass is used to communicate a message through the entire facade. In this building, you can see pictures of flowers that are depicted in the facade of the building, which can use motion pictures in the entire facade. There are several other examples of this where advertising images, things such as stock market tickers, have been used in the facade to communicate to people around and moving around the building. This is one such example of a Chanel building in Tokyo, Japan, where advertising is done in the facade. Another example of functional use of glass in partitions which can turn from transparent to opaque. In a newsroom where the glass is used as a screen to project. Another example where a new model of a car was revealed slowly by converting the opaque to transparent automatically in the interlayer of the glass. Moving back. Now this is as forward as we can go in terms of using glass in buildings. Let's jump down to the basics. How do we use glass in buildings? Now basic glass can be clear, tinted or coated. A tinted glass runs a color through the thickness of the glass. This is by adding colorants in the raw materials to the furnace. So therefore you can get different colors with the thickness of glass itself. Now a further value addition is coating the glass. Now these form the base glass, which are further processed after it's cut to size and ready to go into the building as tempered, laminated, bent or curved. There can be other decorative value additions which is done in this phase, such as a ceramic fret design on the glass or acid etching, frosting. The applications are various and you would see these in day-to-day life. So the glass is transformed and made ready to go into the building and goes either as single glass units or insulated glass units. The insulated glass units are usually 2 or more glasses that are combined with a spacer and made into a single unit. This performs several benefits such as thermal insulation, acoustic insulation, etc. Let's see the properties of glass. Now glass has a very high compressive strength of almost 1000 megapascals. What it loses out in tensile strength, it makes up in its compressive strength. Now the tensile strength of glass 40 megapascals, can be improved by heat treatment. This can be done by a process called tempering, which we will see in the coming slides. Now, the glass itself can be improved from 40 to about 120 megapascals. There are several ways of using glass. Let's look at two of them, the most common. One, it's used as an infill material where the role is to allow vision, and the glass carries the load and transfers it on to the structural members such as the frame. This is using the plate and beam theory, like a slab, where the glass can be used even for flooring, for canopies, roofs, skylights, etc. The second is where the glass itself is a structural member. The glass carries the load and gives the illusion of being frameless because glass is transparent. You see this becoming more and more common today. Normally, we use finite element analysis to study this as a structural member. Sustainability. How can glass be used as a sustainable material? Why do we see more and more buildings that are energy efficient that claim to use glass to actually reduce their energy consumption? This is quite interesting. Let's see how. If you look at total electricity consumption, about 30% of all electricity is consumed by buildings in most countries. If you look within buildings, you have residential and commercial buildings broadly. Now, if you look at this, most of the electricity consumption comes from the air conditioning and the lighting. This is about 80% in both residential and urban residential buildings and commercial buildings. Both of these are directly affected by the glass. Glass allows light and can reduce the amount of artificial lighting used in the building. Most of the heat load on the air conditioner comes from solar heat gains through the glass. This again can be controlled by choosing the right type of glass. It's important to understand the electromagnetic spectrum to see how this heat enters through the glass. If you look at the electromagnetic spectrum, the useful part of the wavelength is between 380 to 780 nanometers. This is the visible part of the spectrum. This is what we want to cause vision, and we want this to enter the building. Now, the near infrared and the far infrared are heat causing radiation. Most of the near infrared comes directly from solar radiation. The far infrared comes from heated objects and surroundings outside the building, which then are transferred through the glass within the building. There's also the ultraviolet part of the spectrum, which can cause fading of furniture, curtains, etc. in the interiors, and is also known to be carcinogenic or cancer causing. So of the total electromagnetic spectrum, the part that we want is only the yellow part or the visible part of the spectrum. To understand thermal transmission better, it's important to understand the parameter of U value. What is U value? It is basically a coefficient of heat transfer. It is the amount of heat transferred due to the temperature difference on the two sides of the glass. How do we define U value? If you take a glass of 1 square meter, for a 1 degree difference in temperature, this could be 21 outside, 20 inside, how much heat actually enters the building? How many watts of heat comes through the building? So let's say, for example, it's 30 degrees outside and 20 degrees inside. So your U value will give you the amount of temperature coming inside. Can we just stop here and shall I explain it on the board? Because it's quite, it can be written down quickly. Yeah? Where's the, and I think I need to wipe my face. No? Any chalk is any chalk.
Subhash, look, Subhash. Which is color choka? In a cut for labu,
okay. Okay. Content marakama.
Very much.
The U value of glass, just to explain to you better on a board. If this is a panel of glass and you have two different temperatures on the exterior and the interior, what is the amount of heat transfer that occurs through the glass? Can be defined by your U value. So if you have a 1 degree difference in temperature for a 6 mm glass, about 5.7 watts pass through the glass. Now let's say you have a temperature difference of 10 degrees. The amount of heat transfer is given by the equation for the heat transfer. So you have the area, it's 1 square meter, the temperature difference is 10 degrees delta, and the U value of 5.7. So you get 57 watts per square meter Kelvin. Now this can be reduced by different measures. One is by doing a coating on the glass, we'll see how later. Another is by making the glass into a double glazed unit. So you have an air gap of 12 mm and you have 2 panes of glass inside. A 6 mm glass would reduce from 5.7 watts per square meter Kelvin to 2.8 watts per meter square Kelvin just by using a double glazing. This can be further improved by doing a coating on the glass. Once a coating is done, a low emissive coating, this can go down to 1.5 watts per meter square Kelvin. This can be further improved by adding a gas, replacing the air inside with another gas, an inert gas such as argon, which would further improve it to up to about 1 watts per meter square Kelvin. Now in this case the 57, if you had used this, would come down to 110 watts per meter square Kelvin. Now this is very important in cold climates where people use heat to actually heat up the interiors, and you don't want that heat to be transferred outside. So let's say it's 25 degrees inside and 0 degrees outside, you have a 25 degree difference in temperature. So most of the heat generated would be lost if the U value of glass is very high. So it's very important to use a low U value glass in colder climates. In a very hot climate where the temperature can go up to 40 degrees or 45 degrees during the day, the U value again becomes important. But if you look like a region like India, where most of the heat gain, most parts of India at least, is through solar heat gain, the amount of heat that is transferred directly through radiation is much higher. Let's look at that now. So how does heat enter through a glass? From the incident solar radiation, a part of the heat or heat causing radiation is directly transmitted through the glass itself. A part of it is reflected, a portion is absorbed by the glass, of which one part is re-emitted inside and a part is re-emitted outside. Now the part which concerns the performance of the building is that which comes inside the building. So your solar factor, or the performance parameter which tells you how much solar radiation is coming in, is the directly transmitted energy and the re-emitted energy compared to the amount of incident solar radiation coming inside, which is given by the solar factor. In some countries, this is also referred to as a G value. Let's see how this affects a building. Consider an average summer day where it's 40 degrees, 38 degrees outside and 23 degrees inside, a temperature differential of 15 degrees. The solar incident energy at around noon is about 630 watts per square meter. This can go much higher. Let's consider a clear glass with a solar factor of 0.83 and a U value of 5.8. Now the amount of heat coming in through radiation would be the solar factor into the solar incident energy. That's 0.83 multiplied by 630 watts, which is 530 watts, 523 watts. The U value into the temperature differential gives you the amount of heat that comes in because of the temperature differential. Now what can be controlled more easily is of course the solar incident radiation by using a solar control glass. So in a tropical country, a majority portion of the heat comes from solar incident energy and needs to be controlled. Now say we used a glass with a solar factor of 0.5 instead of the 0.83. The amount of heat coming in would have been 315 watts and the total heat gain would have been less than 400 watts. Say we used an even lower solar factor of 0.2. The total heat coming through the glass would be further reduced to 126 watts and the total heat gain would be much lesser at approximately 200 watts per square meter. So it's easier to control the performance in a tropical country by controlling the solar factor of the glass. Moving on to the other parameter of glass, light transmission. Now this is a desirable quality to have light inside the building, but then again too much light can be a hindrance to vision and cause glare. On a sunny day you can get around 100,000 lux of light outside the building. Even on a shade, under the shade of a tree on a cloudy day, the lux level goes down to around 10,000 to 9,000 lux. Whereas your light required for working is only 500 lux. Although we have so much abundant light outside, we end up using artificial lighting for this 500 lux. So it's important to use glass effectively to optimize the amount of light coming in so that the light becomes usable by using an optimum light transmission. So the guidelines to selecting a performance glass with reference to tropical countries would be: step 1, reduce the solar heat gain by using a low solar factor or low solar heat gain coefficient glass. Step 2 would be to reduce your U value and thus reduce the rate of heat gain, improve the night performance, and in the case of very hot climates to improve the overall performance. Step number 3 would be to optimize light transmission to enhance daylight and reduce the amount of glare within the building. How are these performances achieved? These are achieved by coating on glass, as mentioned earlier. Now there are two types of coating technologies. One is the online coating and the other is offline coating. The online coating is the older technology which has been in practice for several decades now. The offline coating is a much newer process, and the performance that can be achieved by this type of coating is much better as compared to the online coating. Now in the online coating, the coating is done as the glass is manufactured. So as the glass is leaving the float bath, a coating is done at 600 degrees over the glass by passing a gas over the glass. So this, through the process of pyrolysis, forms a coating on the glass. The newer process is the magnetron process, where the glass is sputter coated in a separate chamber. Let me explain this process on the board. The magnetron sputtering process. Now this is done in a separate chamber called a magnetron coater. This is one such chamber in a magnetron coating line. The number of coating magnetron chambers can be up to 42 or even higher in some cases. Over here, the glass moves over rollers in a very high vacuum environment. The vacuum can be as high as 10 to the power minus 6 torr. After this, a process gas is introduced within the chamber. Argon is the most commonly used gas because of its high mass density. An electric potential is applied within the chamber and the argon gets ionized to form one free electron. Using electromagnets, the argon can be controlled. This is when the target material that has to be coated on the glass becomes important to explain. Now, an engineering coating on the glass can be of several layers. Each of these layers is done in a separate chamber. Each chamber has a target material. to create what is called a coating stack. This coating stack can be engineered to give you any performance in the glass. Let's take, for example, the target material is silver. Silver creates a low emissive coating on the glass. What happens within the chamber is the electromagnetic directs the argon towards the target material, causing the target material to sputter on the glass. Now this creates a nanometric coating on the glass. Because you have 42 such chambers, this coating can be engineered to give you any type of performance. Let's look at a sample coating now. This is a coating that is seen under a nanoscope. You can look at the different materials that have been coated on the glass to give you the performance. The performance can be better understood if we compare it with the online coating. Now, in the online coating, a single gas was passed over the glass, which forms a single layer of coating. What happens is this you have a light transmission of 29, a solar factor of 0.42, which means about 42% of the heat was coming in, and in a double glazing you get a U value of 2.8. If you move to an offline coating, the number of layers increases, so you can actually get a much better performance. So it uses some simple concepts of nanotechnology, such as coating silver. If we had coated silver in a micron thickness, it would have acted like a mirror, whereas if you coat it in its nanometric thickness, the properties change. It allows light to pass through but rejects the heat. Look at the performance of this glass. The desired quality of light transmission is much higher. The solar factor is much lower. In fact, you have about twice the amount of light coming in as compared to the heat, and the U value also reduces. So you get a much better performance by doing an offline coating. Let's see the impact of this in an actual building. How does this affect the energy consumption of the building? This was a study done in Colombo in a building with a facade in the west orientation. Using a clear float was the base case, where you have around 180 units of electricity per square meter per year. Using different performance glasses, using just a low E, the electricity consumption reduces by about 15%, and by using a spectrally selective glass like the one shown to you on the previous slide, the HVAC and lighting consumption can be reduced as much as 66%. Now this directly converts into savings in money and in energy, contributing to both your wallet and the environment. Safety. Let's talk about safety now. Right from when we were children, we were always told when we handle glass to be careful. Let's see how to be careful with glass when it comes to buildings. Now there's safety and there's security. Safety is the more basic, against injury, against glass falling from overhead glass, against fire. Safety is what should be there at all times and is mandated by several building codes. Now moving ahead is security. Protecting against vandalism and burglary, protecting against explosions, bullets, bomb blasts are all considered as security glass. Let's look at safety glass. Now there are two types of heat treatments which are most commonly used to improve the strength of glass. The first one is tempering, toughening, also known as full tempering. The other is heat strengthening. Now tempering increases the strength of glass by approximately 4 times and heat strengthening by 2 times. How do you do tempering? Tempering is done in a separate furnace where the glass is heated back to its molten state at 600 degrees centigrade. Now instead of cooling it in the normal process where it's cooled very slowly, the glass is cooled by forced convection using blowers. So the glass on the surface cools faster than the core. This results in a rearrangement of the layers within the glass. You get a much thicker layer of compression towards the edges of the glass. This creates pre-stressed glass which can withstand a much higher load, but when broken shatters into tiny fragments. The advantage of these tiny fragments are that they are harmless. These can be taken even in your hand without the possibility of being cut, as was the case in annealed glass. Tempered glass is very common. You would have seen these quite often in automotive applications, where the side windows of your car use this type of glass, and in the case of an accident you might even see these pieces on a road. When you compare it with annealed glass, it has a much higher tensile and bending strength. It is much more thermally shock resistant and can even be up to 5 times stronger than annealed glass. In the picture you can see a man standing on a tempered glass pane just to show you the strength. I would recommend you don't do this at home. Another type of processing which is similar to the tempering, just to introduce it to you now, is the curved and bent glass. When the glass is heated up to 600 degrees, it can be molded on frames or pallets and then be bent and toughened. Let's move on to laminated glass, the other type of safety glass. You would have seen laminated glass in the front windscreen of automobiles, wherein the glass has to be laminated by standard. What is laminated glass? It comprises of 2 or more sheets of glass which is bonded by a layer of polyvinyl butyrol. Usually polyvinyl butyrol comes in a thickness of 0.38 and can be used in 1 or more layers. In the event of a breakage, the glass, even though it's broken, remains integrated with the polyvinyl butyrol, and the glass retains a residual strength until it's replaced. This avoids the possibility of glass shattering and falling on people. So it is recommended in the case of inclined glass, glass floors, staircases and roofs. It's also used in guarding applications. Another important quality of laminated glass is that it's used in acoustics to reduce the amount of noise that enters your building. For example, if you're designing a hotel close to the airport, it is supremely important to reduce the noise through your windows. In this case, laminated glass helps reduce the amount of noise coming in. Apart from that, multiple layers of lamination can help with bulletproofing and bomb-proofing your windows. The next type of safety glass is fire-rated glass. You would have seen earlier fire-rated doors and windows are usually fully metal doors with a tiny little window, usually with wired glass. But today you can have fully glass windows, doors, partitions which are fire rated. The main goals of fire protection are life safety, property protection, and continuity of operations. Based on this, glass can provide protection as much as 120 minutes, stopping not only the radiation but also providing insulation, which means you can even stand next to a room where there is a fire. Just to show you some examples of fire-rated doors. Let us summarize what we have seen today. Glass is light. It's not only a light building material, it also allows light into your building. Glass is space. It can create visual connections between rooms and between your exterior and interior. Glass is strength. It has a very high compressive strength, and the tensile strength can be increased by doing heat processing. Glass is luxury. You can use glass for various applications, including premium ones. Glass can be amazing when tempered and laminated, can be used in various applications. An example of a glass floor is shown here. Glass is color. The decorative element of glass done in the processing by ceramic fritting and lacquering can create various colors in glass. Glass is tradition. Glass is emotion, where you can communicate messages through the glass itself. Glass is hygiene. Glass means modernity, gives architectural beauty. It can be integrated to generate electricity. It is used in various solar power generation techniques such as photovoltaics, concentrated solar panels, concentrated solar mirrors, as well as solar heaters. Glass has amazing strength. An example here of a skywalk on the Grand Canyon. With glass, you can achieve amazing complexity. Glass is the modern concrete. Thank you very much. I hope the lecture was informative, and I'll be open to any. Should I say? I'll just start again with the confusion. I'm used to saying I'll take questions, but we can take questions now. Okay. So, thank you very much. I hope the lecture was very informative, and I'll be ready to take any type of questions or comments that you may have. Thank you.